Now let us solve few problems based on the binomial distribution. If given problem is the number of telephone lines busy at an instant of time with probability that a line is busy is 0.1. If 10 lines are chosen at random, what's the probability that first one, no line is busy, second one, all lines are busy, third one, at least one line is busy, and the last one is at most two lines are busy. To solve the problem, first we'll check whether this problem can be solved by using the binomial distribution. And here we are selecting the telephone lines, and when we select a telephone line, either the line is busy or the line is not busy. Since we have only two possibilities, two possible outcomes, the trial is the binomial trial, and we can solve the problem by using the binomial distribution. And in this problem, we are trying to find the probability that no line is busy, all the lines are busy, at least one line is busy, at most two lines are busy. All these terms are related to the line is busy. So let us consider our random variable x as the number of telephone lines busy at an instant of time out of 10 selected lines. Always our random variable x is the number of successes out of n trial, and here we are considering the success as the line is busy, and since we are selecting 10 lines, value for n is 10. Then our random variable x takes the values 0 to 10, and the values are the discrete values, that is 0, 1, 2, 3 and so on up to 10. Our probability of success, that is small p, in this case is probability that a line is busy, and from the given data value for p is 0.1. Then probability of failure, that is q, is probability that the line is not busy, and that is equal to 1 minus p. Since p is 0.1, we are getting value for q as 0.9. And already we know that n is equal to 10. By substituting these terms, we can define our probability function p of x, which is ncx, p power x, q power n minus x. Here value for n is 10, p is 0.1 and q is 0.9. And we are interested to find probability that no line is busy. When no line is busy, value for our random variable x is 0. So we are getting our p of x as 10c0, 0.1 power 0, 0.9 power 10 minus 0. After the simplification, we'll get the answer as 0.3487. Next term is, we have to find probability that all the lines are busy. When all selected 10 lines are busy, value for our random variable x is 10. So our p of x value is 10c10, 0.1 power 10 and 0.9 power 10 minus 10. After the simplification, we'll get the answer as 0.1 power 10. And the next one, we have to find probability that at least one line is busy. When it is at least one line is busy, minimum number of lines which are busy is equal to 1, or it may be more than that. So our random variable x takes the values greater than or equal to 1. In this case, we can consider value of x as 1, 2, 3 and so on up to 10, or else we can use the property that probability of an event is 1 minus the probability of complement of the event. So it is 1 minus probability that x is less than 1. And when x is less than 1, possible value for our random variable x is 0. So it is 1 minus the probability that x is 0. Already we know the value for probability that x is 0. By substituting that, we'll get our answer as 0.6514. And the last one which we have to find is probability that at most 2 lines are busy. When it is at most 2 lines, the maximum number is 2 or it may be less than that. So here our random variable x takes the values less than or equal to 2. And when it is less than or equal to 2, the possible values are 0 or it is 1 or it is 2. Now let us find out probability that x is 0, 1 and 2 by considering value of x as 0, 1 and 2 in our probability function p of x, and after simplifying these terms, finally we'll get our answer as 0.9298. Let's move on to the next one. If the given problem is, in a large number of parts manufactured by a machine, the mean number of defectives in a sample of 20 is 2. Out of 1000 such samples, how many would be expected to contain at least 3 defective parts? And here, by using our probability function of the binomial distribution, what we can find is, in a sample, what is the chances of containing at least 3 defective items or 3 defective parts. But finally, we have to find out of 1000 such samples, in how many samples the expected number. Here we have to find out of 1000 such samples, in how many samples we can expect the sample contains at least 3 defective parts. And for that, first we'll find out the value or chances that a sample contains at least 3 defective parts. And to calculate for 1000 such samples, finally we'll multiply the answer by 1000. First, we'll define our random variable x. In this case, since we are trying to find the number of defective parts, let us consider our random variable x as the number of defective parts in a sample of 20 parts. Then, our random variable x can take the values from 0 to 20. Already we know that always our random variable x is the number of successes out of n trial. So value for n in this case is 20, since we have 20 parts in a sample. The given data for us is the mean value of defectives in a sample. So value for mu is equal to 2. But in our binomial distribution, mu is equal to n into p. Therefore, we'll get value for p as 2 divided by 20, or it is 1 by 10, which is equal to 0.1. And when p value is 0.1, that is probability that the manufactured part is defective, then value for q is 1 minus 0.1, that is equal to 0.9. Now, based on all these terms, we'll write our probability function p of x, that is 20 cx, 0.1 par x, 0.9 par 20 minus x. First, we'll find probability that a sample contains at least 3 defective parts. That is, we are trying to find out for a single sample, not for 1000 samples. Here we are finding probability that a sample contains at least 3 defective parts. And when it is at least 3, it may be 3 or more than that. So our variable takes the values greater than or equal to 3. And probability of that can also be found by using the property 1 minus probability that x is less than 3. When x is less than 3, the possible values are 0, 1 or 2. And now by substituting these values of x, we can find out the corresponding p of x values. And after simplifying the equation, we'll get our answer as 0.323. That is, probability that a sample contains at least 3 defective parts is 0.323. If we want to calculate for 1000 such samples, multiply this value by 1000. So we'll get our final answer as 323. That is, out of 1000 samples, we can expect in 323 samples, we have at least 3 defective parts. Let's move on to the next one. In this problem, 4 coins are tossed 100 times and the following results are obtained. Fit a binomial distribution for the data and calculate the theoretical frequency. And the given results are the number of heads and the frequency. Here we are tossing 4 coins 100 times. Then we are getting 0 heads 5 times, 1 head 29 times, 2 heads 34 times, 3 heads 27 times and 4 heads, that is all 4 outcomes are head, only 5 times. This was the given data for us. And based on this given data, we have to fit the binomial distribution, and then based on the binomial distribution, finally we have to calculate the theoretical frequency. And based on the given data, we can consider the total frequency, that is n as 100, since we are tossing the coin for 100 times, or you can consider some of the given frequency values. And mean of the frequency distribution is given by sigma xi f of xi, or we can consider it as fi, by sigma fi. Now, by substituting these values, we can calculate the mean value of the frequency distribution, and after the calculation, we are getting the answer as 1.96. Always, the table gives us n plus 1 values of xi and f of xi. And in our table, since we have 5 set of values, n plus 1 is equal to 5. From this, value for n is 4. We know that the mean value of the binomial distribution is given by n into p, where value for n is 4 and mean value is 1.96. Now by simplifying this, we'll get value for p as 0.49. And when value for p is 0.49, our q is 1 minus 0.49, that is equal to 0.51. Now, by using these values, let us write our probability function p of x, that is 4cx, 0.49 par x, 0.51 par 4 minus x. The theoretical frequency is given by the product of the total frequency and the probability function values, that is n into p of x. In this case, n is 100 and our p of x is 4cx